Hi, this is a lecture on section 1.1, a brief overview of differential equations. I'm actually going to turn off my cam for the majority of this recording, but I wanted you guys to be able to see me at the beginning. So let me share my PowerPoint. Okay, so the first thing that we want to go through before we dive deep into differential equations is what the heck is a differential equations to begin with? So definition, a differential equation, or we can abbreviate that as DE for short using capital D, capital E, is an equation containing some or all of the following: an unknown function, the independent variable of the unknown function, at least one derivative of the function, and one or more constants. The constants are also called parameters, and the function itself is called the dependent variable. So you guys should be fairly familiar with some of this verbiage, as to be in differential equations, you've taken quite a few math classes up until this point. So if you remember function notation f of x, where x was known to be the variable, the input of the function or the independent variable, the f is the output of the function known as the dependent variable. Here, our variables are also functions. And the how you know which one is the dependent variable or of the function, you would look for which one of the functions is being, um, the derivative is being taken. Couldn't get that out. So for example, if we look at the very first column, here are some examples of some differential equations, and I did them in several different forms or different notations, different variables that I used. So here we have a definition of an order. So the order of a particular differential equation is the number of the highest derivative that's in the equation. So for this first row, I have x of t and 2 primes is equal to negative c over m times x of t 1 prime minus g. Now, because this is function notation, so we know that this is the output or the dependent variable, that's why x is here. And inside the parentheses, we know in function notation is the independent variable. So I have identified t as my independent. Everything else that appears will be parameters, c, m, and g. And I know that it's order 2 because I have a first derivative and a second derivative, and the order takes the highest of the derivatives. Row 2, I have y double prime plus 4y equals sine of t. Well, because y has the derivative, or in this case, a second derivative taken, I know that y is my dependent, t is my independent. There are no other parameters in the equation. And because it's a second derivative, it's order 2. Y prime plus ay equals e to the negative x. So again, because y has the derivative, we know y is the dependent. X is inside of a function, a known function. So I know that x is my independent, not the a. A is a parameter, and there's only a first derivative, so it has an order of 1. In this last example, it's not as obvious. So I can clearly see which one's the dependent because x has the derivative on it, so therefore x is the dependent. But there is no independent. Okay, b is a parameter, a is a parameter. Why aren't those the independent variables? Okay, so, and that boils down to more, what do we use in general? So typically when you're using y for a dependent variable, you use uh, either x or t for your independent. And when you use x for your dependent variable, you will never typically use y for your independent. You would use t for your independent. So the independent is not always visible. And that's when you default to that rule of thumb that y, the typical independent, would be x, sometimes t. X, the typical independent, would be t. So a solution to a differential equation is a function that when substituted into the differential equation for the dependent variable results in a true statement. In other words, it means that the left side of the equation is exactly the same as the right side of the equation after algebraic manipulations for all values of the independent variable. So now let's try an example. So let's verify the following solution. So let me jump to my whiteboard. Okay. And let's do this verification problem out. So the problem stated that we have the differential equation dy dx is equal to x y raised to the 1/2 power. With the solution, they're stating a solution to this differential equation is y equals 1/16 x to the 4th power. And they want us to verify that this is a solution. So recall that the definition of a solution for differential equations means that the left side of the differential equation matches the right side using the solution for all values of the solution. So let's start with the left-hand side then. Left-hand side, LHS stands for left-hand side. That's commonly used when you're writing out proofs to represent left-hand side versus RHS, right-hand side. So the left-hand side of the equation is dy dx. Okay, essentially that's just a fancy way of writing y prime. They mean the same thing. It's the derivative of y with respect to x is how you technically would read it. So that means I need to take the derivative of y. Well, here's y. So let's find the derivative, y prime, or dy dx. Remember, you have to recall now, bring back those calculus days. You take the exponent, you're going to bring it down, multiply in front, come back up and subtract 1. That is the power rule. So that gives us 4/16 x cubed. Reduce 4/16, we get 1/4 x cubed as the derivative of our potential solution. So we're saying that dy dx is equal to 1/4 times x to the 3rd power. Now what we need to show is that the right-hand side of the equation produces the exact same result. So right-hand side. The right-hand side of the equation is x times y to the 1/2 power. There are no derivatives on the right-hand side, so I don't need to take any derivatives now. But what I do need to do is I need to substitute rather, the y for 1/16 x to the 4th. So I see that y is equal to 1/16 x to the 4th. So I need to substitute this equivalent expression in x for y into the equation. So I get x times 1/16 x to the 4th raised to the 1/2 power. Now, laws of exponents allows me to distribute the 1/2 power, which is essentially just a square root. So I get x times 1/16 to the 1/2 power times x to the 4th to the 1/2 power. Now, this gives me 1 over the square root of 16, which is 1/4. And now I have x, which is from the first part here, and x to the 4th to the 1/2. Well, when you have power to a power, the laws of exponents tells us to multiply, and 4 times 1/2 is 2, so that would be times x squared. Now, laws of exponents tells me that same base times same base, we add the exponents, resulting in the right-hand side being, I'm going to put it up here, 1/4 x cubed. Since my left-hand side of the equation has successfully matches the right-hand side, I have completed my proof. I have verified that the given function is a solution to the given differential equation. Sorry for the messiness. It is not necessarily the easiest to draw on these whiteboards. Let's try the next example. So without jumping back to the PowerPoint, I am just going to jump to the next example. Okay. And we're just going to do it on our whiteboard. Okay. So the next example is to verify the solution for the following differential equations. The second derivative of y double prime, minus 2y prime plus y is equal to 0. That's the differential equation. And the given solution to verify is y equals x e to the x. Okay, so same process that we just did. We need to prove that the left-hand side is equivalent to the right-hand side. Now for us, our right-hand side is just a 0. So that should make at least the right-hand side really simple. I just pretty much have to show the left-hand side is also equivalent to 0. So we need a second derivative and a first derivative to work with this left-hand side of the equation. Y double prime minus 2y prime plus y. So I'm going to come over here to the right side of my board, and I'm going to first calculate the first and second derivative to make it easier to make a substitution. So this is a product rule. Okay, we have the function x, or the variable x, times the function of e to the x. So remember the product rule. You have the first times the derivative of the second plus the second times the derivative of the first. But the derivative of the first x is just 1. So that gives us our derivative to be x e to the x plus e to the x. Okay, excuse me for the pause. So now we have the second derivative to do. So again, we already know what the derivative of this term is because we just did it. So we know it's x e to the x plus e to the x. Plus, we need the derivative of the second term. And the derivative of e to the x is just e to the x. So if I make that a little smaller, it's going to be x e to the x, or I should say simplified. These are the same terms, so there's 2 of them. Okay, so now I have my first derivative and my second derivative, which will make it much easier for me to substitute into the left-hand side of the equation. So we have second derivative, which is x e to the x plus 2e to the x minus the 2 times the first derivative, which our first derivative was x e to the x plus e to the x. Now let me erase some of this stuff out of my way as I'm running out of room. There we go. Okay. And then we have plus y, and this is y. So we have plus x e to the x. So my parentheses show you all the substitutions I made. I made a substitution for the second derivative of y, and a substitution for the first derivative of y, and a substitution for just y. Now, this is a bunch of craziness. At first glance, I'm like, this is not going to be 0, but you never know because we have a bit of algebra to complete. So we have here x e to the x plus 2 of these e to the x's. To distribute here, we have negative 2 of these x e to the x's and negative 2 of these e to the x's plus an x e to the x. So here I have positive 2. Actually, let me put this in a different color. I have a term of positive 2e to the x's and a term negative 2e to the x's. So those cancel. I have 1xe to the x, 2xe to the x's, and 2 negative xe to the x's. So these all cancel, giving us 0, which also happens to be the right-hand side of the equation. I have successfully shown that y equals xe to the x is indeed a solution to the differential equation y double prime minus 2y prime plus y equals 0. Okay, now let's go back to our PowerPoint. This is the example we just worked out. Definition of a general solution versus a particular solution. So a general solution of a first order differential equation is a solution with one constant that does not appear in the original differential equation. This is also called a one-parameter family of solutions. When a particular value of the constant is chosen, we get a particular solution. Now, some of these definitions, I do have to agree, are not the easiest to understand when you're reading them in a paragraph, which is why examples are so super helpful. So consider the differential equation, the one we just worked with. The general solution, notice that the C1 and C2, those parameters are general. They're not specific values, hence the name of the general solution. And the particular solution is when you have found specific values for C1 and C2. The definition of an initial value problem. So an initial value problem, which is very commonly abbreviated IVP, all caps, consists of a differential equation or system of differential equations along with a sufficient number of initial conditions to determine the arbitrary constants in the general solution to the differential equation. When there is more than one initial condition given, they must all be given at the same value of the independent variable. A solution to an IVP problem, well, I guess it's initial value problem. I don't have to repeat IVP problem because that's technically saying initial value problem. Just saying. Is a function which satisfies both the differential equation and the initial condition or conditions. Let's try one. So again, I'm going to jump back to my whiteboard for the next 3 examples. All of them are, I guess maybe not all of them. We're going to be taking a look at 2 initial value problems at the start, and then we'll start talking about some other types of problems that we can also solve. All will be done on the whiteboard. So let me jump back to our whiteboard. Let me clear this out. Okay, so we are working on a problem where we're given the differential equation y prime equals y. And the given initial value problem uses a solution y equals c e to the x. So that's the general solution. It's general because c does not have a specific value inputted for it. And we want to find that particular solution by using the initial condition y of 0, that's a 0, equals 3. Okay, so we know that the independent variable is 0, the dependent variable is 3. So x is 0 and y is 3. So in order to find a solution to the IVP, we are going to take a look at the solution y equals c e to the x, the general solution, make these substitutions. So the y is 3, the e is 0, and we solve for c. It's as simple as that. So e to the 0 is just 1, so c equals 3. So that gives us the particular solution, solution to be y equals 3e to the x. That is the particular solution for this initial value problem. Now the next example. And if you have the PowerPoint up with you, you would see that the next example is a second order initial value problem where the differential equation is x double prime plus 16x equals 0. And given the solution x equals c1 cosine of 4t plus c2 sine of 4t, and the initial value is set at x of pi over 2 is equal to -2. So we have our input and our output. Now we also have, since it's a second order, we need to have the first derivative initial value point as well set at pi over 2. So if you were confused by that definition where it said if you have multiple initial values, they all have to have the same independent, notice that the input is both pi over 2 for the x function and the x prime function. And that's what it was referring to in that definition. That if they're going to give you multiple initial values in order to complete the problem, the independent variable has to be the same. So let's work on this problem. So first, step 1 is to take a look at the solution. X equals c1 cosine 4t plus c2 sine 4t. And we're going to need the first derivative as well. So the initial value pertains to the original function, solution function, and the first derivative of the solution function. So let me clear this out real quick. So what we're looking at is x equals c1 cosine 4t plus c2 sine of 4t. Now, the first thing that I want to do is I want to take the general derivative, so x prime. Now, the derivative of cosine is negative sine. And you keep the inside function, so essentially I'm applying the chain rule right here. And then take the derivative of what's inside. So 4t is the function inside of sine, and the derivative of 4t is 4. And I'm just going to place the coefficients in front because they're easier to work with there. The derivative of sine is positive cosine, same thing. The positive cosine and the inside function is unchanged. Then you take the derivative of what's inside, which is 4, and we put all our coefficients up front. At least I do, because it makes it easier to look at. That's what we're most commonly used to looking at. Now that we have both the function solution and the function solution's derivative, we can use our initial values. So for the function, it told us that x of pi over 2 is equal to -2. So what does that mean? It means that -2 is the output, so I'm putting it in for the x, is equal to c1 cosine of 4 times pi over 2, our input, plus c2 sine of 4 times pi over 2. We're going to have room to do double parentheses on that last one. So if we simplify, we have -2 is equal to c1 cosine 4 times pi over 2, which is just 2 pi, plus c2 sine of 2 pi. Okay, now it's a question of what is cosine of 2 pi? Cosine of 2 pi is 1. Sine of 2 pi is 0. So we have -2 is equal to c1 times 1 plus c2 times 0. So it's telling us that this c2 cannot be found using the original function, and C1 is equal to -2. Now, this is exactly why we were given an initial value for the first derivative, because we cannot get C2 from this initial value from the original function. It disappears when we put in our values. So now let's use the first derivative and calculate C2. So let me make a note here that we found that C1 is equal to -2. Now let's take a look at the derivative and solve that one. Give me a minute to erase. My finger is not the best eraser, but that's what we got to do. Best I got. Still erasing. Oh, missed some. Okay. Now, our second derivative, the initial value that was given was x prime of pi over 2 is equal to 1. So we are saying that 1 is equal to -4c1 sine of 4 times pi over 2 plus 4c2 cosine of 4 times pi over 2. Now, we already know that 4 times pi over 2 reduces to 2 pi. Let me just write that in real quick so we have all the steps written out. We know that sine of 2 pi was the one that went to 0. So this gives us times 0 plus 4c2, and we know cosine of 2 pi is 1, which means that our c1 this time disappears, and we have 4c2 is equal to 1. So we have to continue solving that. We have 4c2 is equal to 1. Divide by 4 on both sides, and we get 1/4 is the value of C2. So now what we got to do is we got to put it all together, and we have to enter C1 and C2 into the original solution. So the original solution again was x equals C1 cosine of 4t plus C2 sine of 4t. And now our particular solution is x equals -2 cosine of 4t. Notice it doesn't matter if I use parentheses after the cosine or not. It's assumed there's always something in the cosine function, or it's not a function, it's just the word cos, plus 1/4 sine of 4t. And that's an S. And that's our particular solution for this initial value problem. Now, the next example up is finding, let me move forward, here we go. So the next solution, the next example that we are going to cover in the PowerPoint, and I'm not going to jump back to the PowerPoint, but we want to find values of the letter M so that the function y equals e to the mx, y equals e to the mx is the function we're working with. We want to show this as a solution, or we want to find the values of m so that this function is a solution of the differential equation 5y prime is equal to 2y. So now we need to figure out what values of m will work. It might be one value, it might be multiple values, it really depends. So we'll just have to solve it to find out. So now the first step would be to look at the left-hand side of the differential equation. So now the left-hand side of the differential equation is 5y prime. So in order to do anything with this side, I need to find y prime. So I'm going to take my solution, y equals e to the mx, and take its first derivative. Now the function e its derivative is exactly a copy times the derivative of what's inside. M, remember, is a parameter times the variable x, so it's like a coefficient, and the derivative of mx would just be m. So I'll multiply that in front because I like to put my coefficients in front of my functions. So now my left-hand side is 5 times m e to the mx. That's what I get on the left-hand side. All right, now let's take a look at the right-hand side. There's not a whole lot I can do to simplify the left-hand side besides just dropping the parentheses. So the right-hand side is 2y. All right, well, I already know what y is. So that I'm going to replace the y with this function, e to the mx. So the left-hand side of the equation is 5me to the mx. The right-hand side of the equation is 2e to the mx. They're not the same yet. How do we make them the same? Well, we have to find m that satisfies both these sides. That's the whole point. We need to now make the left-hand side exactly equal to the right-hand side. So let's do that. Let's set them equal. Our left-hand side, we calculated it came out to be 5me to the mx. And we want to set that equal to the right-hand side that we have discovered was 2e to the mx. And now we want to solve for m. So I look on both sides of these equations. They're both being multiplied by a factor or a function e to the mx. So if we divide by e to the mx on both sides, they go away. That leaves us to a much simpler equation to solve. We divide by 5 and we get m is equal to 2/5. And that is the value for m that makes the function y equals e to the mx a particular solution for the differential equation 5y prime is equal to 2y. Let's try one more of these examples. So how about we try another one where we're looking again for the values of m, but this time the solution function is y equals x raised to the mth power. And the differential equation is x, y double prime plus 2y prime is equal to 0. So the hard one is going to be the first one up, which is the left-hand side of the equation. And before I even get to the left-hand side of the equation, let's take our derivatives, because I can already see that I have a second derivative and a first derivative in here. So y prime, okay, x raised to a power m. So we'll do our power rule, and that would give us, bring the m down in front, come back up, and subtract 1. Second derivative, bring the power down. So now we have m times m minus 1, x, subtract 1 gives us m minus 2. Okay, so now I have the first derivative and the second derivative. It'll be much easier for me now to make a substitution into the left-hand side of the equation, being x times y double prime plus 2y prime. So x times double prime is going to be times m minus 1, x to the m minus 2, plus 2 times y prime, which is m x to the m minus 1. Okay, I've made my substitutions. Now I'm really not sure what to do with this. So I look at the right-hand side of the equation and I see, okay, I'm just going to be setting this equal to 0 and then solving for m. So I probably want to do some sort of simplifying to make my life a little easier to do that. So let's rewrite it again. The left-hand side of the equation that we just made the substitutions for was x times the second derivative plus 2 times the first derivative. Now, The only simplifications I can see right now is to distribute in this m, maybe drop the parentheses here. So I have x times m squared minus m, x to the m minus 2 plus 2mx to the m minus 1. All right. Now I have in question, I have same base times same base. Remember with our power rule, when we have same base times same base, we use an operation of addition to our exponents. And this has an exponent of 1. This has an exponent of m minus 2. So we're doing 1 plus m minus 2. 1 minus 2 is -1, so this reduces our exponent to m minus 1. So now we know our left-hand side is m squared minus m times x to the m minus 1 plus 2m times x to the m minus 1. So now I know that I have two like terms with different coefficients. So now I want to set this equal to the right-hand side. So now we want to take this simplified left-hand side and set it equal to the right-hand side in order to attempt to solve for m. So our left-hand side, our newly reduced left-hand side, m squared minus m times x, I don't know what kind of x that was, times x to the m minus 1 plus 2m x to the m minus 1. And set it equal to the right-hand side, which is 0. Okay. Now our goal is to solve for m. So let's not try to get too overzealous or crazy on this. One thing that we notice is that they both share this exact x. So let's factor that out. So I'm taking x to the m minus 1 out in front, leaving me with m squared minus m plus 2m, still equal to 0. Now, if you remember the zero product property from algebra, it states that if two things are being multiplied and they're equal to 0, specifically 0, then one has to be 0. It's impossible to multiply two non-zero numbers and get 0. That's just a fact of the number 0. So that means that x to the m minus 1 is equal to 0, or m squared minus m plus 2m. Well, let's combine that. Combine like terms. We have negative m plus 2m just gives us minus m is equal, plus m is equal to 0. Now let's talk about this x raised to an m minus 1 is equal to 0. Can anything raised to a power ever be equal to 0? Well, the only way that that's possible is if x is 0 itself. If that's the case, then that has nothing to do with m. And we would not be solving for m in this part, because the only way that this is true is if x equals 0. Well, that's not going to help us solve for m. So we're going to throw this one out because it's not very helpful. So now we're going to solve this one on the right side. This one looks more promising. Let's factor out an m. And again, we have a zero product property where we can set each one equal to 0 separately. So the first part of the product is m. Set that equal to 0. That is a value for m that will work. We set m plus 1 equal to 0, subtract 1 on the other side, and that gives us m is equal to -1. So we have found that there are two values of m that will allow this function to be a particular solution to the differential equation. So this concludes our basic overview of differential equations, giving you a taste of what the heck a differential equation is, what does it mean to be a solution, and the difference between a general solution and a particular one.